All right, so 22.1 electric forces for chapter 22 going into electricity. But to start with, just talking about the most basics of charge that in the universe we have negative charges and positive charges. And they all come in some integer quantity of E. So the electron, which is what we think is one of the smallest particles, has a charge that is that number, and charge can only come in integer multiples of this value. So the electron, you can't cut the electron in half. So you'll never have, say, a half of E. You'll never have, say, 2.7 of E. Charge, we say, is quantized. It always comes in some integer quantity. So that means you'll have like 4E or 100E. It's always an integer value of the charge you have. And that's what we see in the universe. We say all charge is quantized, that the electron has charge minus E, and then the proton has charge positive E. And again, you can't have a half of a proton, can't have half of an electron. So, if you've got 3 protons, then you have charge 3E. And, if you throw in 2 electrons in there, which has charge of minus 2E, well, if you add all that together, the total charge would just be 1E. So we say charge is quantized, always comes in these units of E, and there's never a half of E. You can't cut a particle or a proton in half and half its charge. It's always going to be an integer multiple of E. And they're also saying here, by showing these wires, they're just making a statement. I think everybody's heard at this point that like charges are going to repel each other. So two protons, both positive, they're going to repel. Just like 2 electrons, if something is both negative, they repel. What attracts is if they're different charges. That's when they'll attract each other. And then that's how atoms form and all our molecules. It's because these will attract each other. They'll go around in their orbits to form the matter we know today. But that's what they're showing here with just these kind of hanging charges on a wire. Just talking about that basic idea that like charges repel, opposite charges attract. And that's what they're just trying to show here. Also trying to show that these things, I know they don't quite say it, but these things are both negatively charged. Negatively charged things repel each other. So as they bring their straw in closer to this one, the hanging straw vibrates a little bit because it's being repelled, because they're both negatively charged, and then they'll repel each other. And they're just talking about, these are plastic straws rubbed with wool. If you rub a plastic straw with wool, causes it to be negatively charged, and that's what that picture is. They're just trying to show that negative charge repels each other. So not too much there. 22.2 electric charges. So this is where they're talking about more of the atom, and this is a basic picture of an atom that is pretty common today, where we say there's some nucleus and then the electrons orbit around it. And that's a simple picture. The actual picture is a lot more complicated because particles have wave-like behavior at the atomic level. And so it's more that, a better picture of an electron is that it's more of a wave that orbits around than it is just a particle in an orbit. But this is a simple picture we like to draw, just to convey the idea, really, that at the nucleus is where we have the protons, the positive charge, and then what orbits are the electrons, the negative charge. So even though a proton has the same charge as an electron, they have the same charge, the proton is actually much, much heavier than the electron. So if you're just looking at the picture here to the right, wondering why it's the electron that orbits and not maybe the positive charge. That's because the protons are actually much, much larger, while the electron is just this tiny little thing. And so that's why the electron ends up orbiting the positive charge. And in this picture, they also have these yellow circles that have no charge on them. Those are our neutrons. And neutrons are again, they're actually pretty large particles, about the size of a proton. But they have no charge on them. And it's part of the strong forces that hold the nucleus together, the neutron. We won't talk about that too much, mostly about, charge in general, meaning plus or minus charge here. But at the nucleus scale, this very tiny part here, that's where the strong force comes in, another force of nature that really beyond our experience as humans, because it's, our body is made up of just trillions of these atoms, and really hard for our eyeballs to see the exact center of one of these. Another thing about this picture, that the nucleus and the electron, an atom is actually mostly space, is really what an atom is, mostly open space, and you have this kind of tiny center and an even tinier particles orbiting around it, and a lot of open space is actually matter is made of a lot of open space. Another thing they're trying to talk about with this picture is that if you have these two positive charges in the middle, and then you have these two negative charges orbiting, that the total configuration here, we would say has charge 0, because you just add all those together, you got 2 positive and 2 negative, and then when you add it all together, you have a total charge of 0. And that is really common for the state of matter. Matter tends to prefer having a neutral charge overall. In other words, the atoms are designed in a way so that they have the same number of protons at the center as they do electrons orbiting. So if you have some atom that, say, has 10 protons at the center, then chances are it has 10 electrons that orbit it, so that it has a total net charge of 0. And that's the balanced state matter likes to be in, although it doesn't have to be, because you can always knock off one of these electrons for, energy might come in and knock off an electron. And in that case, you'd have 3 positives and now only 2 electrons. So this would result in a positive charge then that would happen, because you'd have more positive than negative. Ultimately, that's what we call ions. Ions are when the atom is not neutral. An atom then has a charge to it when we call it an ion. So that means the charges here just aren't balanced. And that seems a little specific. Well, there's a homework question about ions. So just try to remember that matter does prefer to be in a charge, total net charge of 0, but things can happen that knock off an electron and leaves the atom in a state then it's not neutral anymore. It may have more positive charge or more negative charge, and we call that an ion then when its charge isn't 0. And this is last part here, the saying, if positive charge repels itself, like at the nucleus, these positive charges do repel each other at the nucleus. But again, there's a strong nuclear force that overcomes that repulsion, is what ends up happening at the nucleus. So we're talking about just the electric field charge, which means from plus or minus charge. Nothing in the book is actually talking about the strong nuclear force that holds the atomic center together. So just throwing it out there, that's not in any homework questions or anything, but if you're wondering how those plus charges actually stay together when they're repelling each other, well, that's because there's another force, the strong nuclear force, that then overcomes the electric field to hold those together. So that was 22.2, conservation of charge. So it's another thing that, if you think of, say, I always like to start with water because it's a nice example, but if you think of a hose and you push water into one end of the hose, Well, where's that water going to go? Well, the water doesn't disappear. New water doesn't magically come into hose. All the water that goes into the hose must come out of the hose. And we call that mass conservation, that the mass that goes into the tube must be the mass that comes out of the tube. That mass just isn't created somewhere magically in the tube or just disappears. And the same thing is true with charge, that if you have, say, 2 electrons that go into this tube, then it must be 2 electrons that come out of the tube. And we say charge is conserved, that the charge you have is what moves around. There's no magical blinking in of existence of some charge or no magical taking away of a charge. The charge goes in, has to be the charge that comes out. We call that charge conservation. And what's our little bubble here? Charge is like a baton in a relay race. It can be passed from one object to another, but isn't lost. So, yeah, that's a good statement. Now, electrons can jump from material to material if they're close enough. But overall, that statement, good statement. Charge is neither created nor destroyed. It just moves around. And you're saying here, a neutral atom, there is as many electrons as protons, so the net charge is 0. Atoms prefer to be in a neutral state. And they say if an electron is removed, so that's again, if an electron gets knocked out of the atom, then it becomes positively charged. And here's where they say a charged atom is called an ion. So an ion is when it's no longer neutral. And another common example of taking wool and maybe rubbing a glass rod tends what to be happening, or they're using fur in a rod. So when you take wool and rub it on a rod, that actually knocks off some of the electrons from the wool, sticks them onto the rod, ends up making the rod electrically charged negatively. That's why they got the little negatives around the rod here. And you've now negatively charged your rod. And this has been actually known for thousands of years. I think even the ancient Egyptians knew that if you rubbed certain materials, it would have some strange attractive property, because, they didn't know about electricity or magnetism. Really wasn't until the 1800s that humans really started to grasp the idea of electricity and magnetism. So, back in ancient Egyptian times, I'm sure this was something that was probably very magical or interesting to them. But it's actually been known for quite a long time. Same as static electricity. People have known for a very long time that you can get little sparks by touching things or touching people. And I have no idea what ancient Egyptians thought about static electricity, but they knew it existed, though. And let's see, what's this? FYI, static electricity is a problem. Also, static electricity, again, known for a long, long time. At gas pumps, even a tiny spark can ignite gasoline vapors and cause fires. Are frequently lethal. Good safety rule is to touch metal and discharge static charge from your body before you fuel. Definitely good advice. I'll have to say that static electricity blowing up a gas station is not a very common occurrence. But that is a good safety measure. So what happens if for some reason you feel your body's charged negatively, or you're feeling like you may notice, like, if your hair is acting a little staticky or something, if you touch a metal surface, that metal surface will actually allow that extra charge to go into the metal surface, and it leaves your body, so you can bring your body back to a neutral state. And that's what your suggestion here. If it is, I'm not going to deny it's not a good practice to touch the metal of your car before you pump your gas. That is definitely a good safety procedure. But in the long run, gas stations blowing up from static electricity, just not a very common occurrence. Let's see what else they got. Coulomb's law. So, actually in physics 131 and stuff, this is where we start with electricity, and there is the equation. This may be, I think this is the only equation we have here. So Coulomb's law, F being the force. So the force particles feel is actually this K, which I'll talk about in a second. You have charge 1, charge 2, and divided by their distance squared. Now in physics, R is commonly used for distance, and there's various reasons for that. But if you're just wondering why is there R for distance, it's something pretty common in physics to use R. And actually use the word right here, radial distance is why R tends to get used, because of the radial part there. K. Now K is about 9 times 10 to the 9th, this number. K, though, is 1 over 4 pi epsilon naught, where this epsilon naught is a physical constant of the universe. So this force here, how strong this force is actually based on this physical constant. So if you change this value called epsilon naught, if you change it, then you change how strong the force is. And thus far with humans, we have absolutely no ability to change this value. That's why we call it a physical constant of the universe. That seems to be something we can't change. That when you have two charges, they will feel this force, and there's nothing we can do about it. We can't change its strength or make it weaker, and so we call epsilon naught a physical constant. However, just to be clear, for our book, they're only going to use K, though. I just wanted to give you a quick idea where K comes from. It does come from a physical constant, but for us, we're just going to use 9 times 10 to the 9th for K there, and that'll be good, because that's ultimately what this number approximately equals. And then what charge we have, we'll put charge 1 here, we'll put charge 2 here, and then we will probably have a distance of separation we put in there, and then we can figure out the force in newtons that these charges have. And Coulomb actually figured this out experimentally, this result, and it's something I always like to throw out there, that it's not like these equations are just made up and people hope they work. These are observations people made over many years of what the patterns of nature are. And Coulomb found this pattern of nature, and it happens to be a mathematical statement, which pretty much all of physics is mathematical statements. Sure. Awesome. Yeah, I don't know if I'd qualify it as awesome, but definitely a rule of nature. Coulomb's law is like Newton's law of gravity. It is, well, oh man. I consider that a dangerous statement. Now, the reason that they say that, because here is Coulomb's law. We call this an inverse squared function. If you recall, the force of gravity looks mathematically very similar. Actually, mathematically, we would say it's even the same function. So here's gravity. Here's the electric force. They are identical math functions. Now, they do have different numeric values, like G is another universal constant, while the electric field has epsilon naught for its universal constant. So these give different values, and the math of them is, they're the same function. They're both inverse square laws. However, the electric field and the gravitational field actually act very differently. And that should be maybe immediately apparent, because there's no negative mass. And this is something physics still explores, if there is negative mass. I know there was, I think it was about a month ago, that antimatter, another form of matter, but there was some curiosity if antimatter might have negative mass. And so here in America, I don't remember at which institute, but they created a bunch of antimatter and they created it in a tube. And then they watched as this antimatter was in the tube, because if it was negative mass, it would float up. But it turns out it fell down to the earth like we would expect positive mass to do. And so physics today still experiments around to see if there's evidence for negative mass, but we have yet to find any. This is a big difference, because with gravity, we're saying positive masses attract. Positive masses attract with gravity, yet positive charges for the electric field repel each other. So I'm just looking at this statement again. Coulomb's law is like Newton's law of gravity. I would argue that's only true mathematically speaking. Mathematically speaking, they are both inverse square laws. However, the physics of them is very different, though. And that's just some little addendums they have to 3 and 4 there. Let's check out what is next. Conductors and insulators. So matter, like the table I'm writing on here. Matter forms in various structures. The easiest one is probably just a standard cube structure. And the circles here are the atomic sites. So I'm drawing the circles. This would be the atoms. And these are the bonds that hold them together. And sometimes mass will form into this type of structure. There's different structures that they can form into. Sometimes they can form into that shape or other shapes that are maybe different. Actually, I just did a square that was a diamond, but different configurations that matter can form into depends on some of the properties of the atoms and stuff. But let's just say we have a nice square lattice like this, and that's what, say, my tabletop is made of that I'm writing on right now. It's this square lattice of all of these millions and billions of electrons that ultimately form my table, or these atoms. And we're talking about these two things here, a conductor and an insulator. And these are, in a sense, the opposite sides of the same coin. And what I mean by that is these atoms all have their electrons orbiting them. But for some materials, these outer electrons are loosely bound to the atomic site. And so for materials that have this electron loosely bound, so if it's loosely bound, did I just write, what is that word? Loosely. I put 2 S's there. If it's loosely bound, then they move around actually quite easily, and they'll move through the material. And we call this a conductor then. So a material that has its electrons loosely bound means those electrons can actually float around in the material. And then we call that a conductor. So when electrons can move around in a material, that's how we get a current to flow. Now, the other type of material we're talking about is an insulator. An insulator, I'm just going to draw, another square lattice structure again. For an insulator, the electrons are tightly bound. So these would be tightly bound. And when they're tightly bound, they don't like to move. And they're just going to hang around on their atomic sites. And when electrons just want to hang around on their atomic sites, we can't get electricity to flow through these materials then. Because electricity, most commonly, I have to say that, is electrons. So electricity isn't always electrons moving, but most commonly it is. And so if electrons will move, we'll get a current. If electrons can't move, we get no current. And so we just label these types of materials. Conductors, that's what wires are made of. You know, the circuit board for our computers and electrical devices all contain conductors in them, so the electricity will move freely. While insulators are used to not to prevent electricity flowing. And that's, I'll just scroll through here, but that's, I'm sure, the main point. They even mentioned semiconductors. Well, let me get back to the second, I guess. And superconductors, wow. All right. So I guess I won't get any more specific on that because they aren't, but they're going. So these are two types of materials: conductor, loosely bound electrons, current flows. Insulator, tightly bound electrons, current can't flow. Now, the next one we're talking about is a semiconductor. So a semiconductor tends to be an insulator when it's just hanging around, but you can give it some voltage or do some stuff that will force the electrons to be more loosely bound and then allow current to flow. So semiconductor, also very useful because on one point it can be an insulator, yet on the other point it can be a conductor. And then, as you know, as humans are clever, we could do all sorts of stuff with that. By clever meaning, I know, I'm talking to you through a computer, over the internet, through the monitor. All that stuff is a result of our ability to control electrons. Superconductors, transistor is a circuit element. They don't really say much about it. I'm not going to either. Transistor is simply one of the circuit elements. There's resistors, there's capacitors, there's transistors, there's inductors, there's diodes. And transistor is just a circuit element that has a lot of stuff you could do with it. Superconducting is actually where I did my PhD research on superconducting because I think it's fascinating. But in superconductors, so a superconductor is another state of matter, we say, like how there's solid, liquids, and gases. That's the common three you're probably familiar with. There's also other states. The superconducting state is another state of matter, we say. And what happens here is if you get a material so incredibly cold that because electrons do behave like waves, that when you get things very cold, the electrons then can move through the material effortlessly. And there's eventually then no resistance. So now, this is going to things that are more quantum mechanics. When I say particles behave like waves, this is a fact of the universe. But imagine that we're looking down on an ocean and water's coming in. So we're on an ocean and there's some pull in the way. Well, if there's some pull in the way, the water, just pretty effortlessly goes around it. And it's not like water is a particle that hits the pull and then bounces back, because water behaves like a wave. And a wave has it's very easy just to flow past this pull in the water. And that's kind of something what happens with superconductivity is that when you get something extremely cold and the wave nature of matter starts to dominate, then the wave nature can flow through the material very easily, and there's actually no resistance then. And this has so much potential for the future. Still a long ways away, though, because superconductivity has to be so incredibly cold. Means it's actually very expensive, to create a product with it. But computers have little switches in them. That's what the CPU has. It's always switching. And we call this solid state switches, meaning that they're not superconductors. But these switches that are in the computers can only switch so fast because eventually things get too hot and they won't operate anymore. If we can make new switches with superconducting material, we can make these switches so much faster than our current computers today. So one of the things superconducting can do is help us make much faster computers. And just want to throw out there, if you do know something about computers, a superconducting computer is different than a quantum computer. A quantum computer is when you're dealing with a qubit, which means you have a qubit that can have 3 states, versus our traditional computers, which is just binary, can either be in a state of 0 or 1. A superconducting computer is still a binary computer using 0 and 1, a superconducting computer. It would just have much faster switches in it, and so it would be faster than our traditional computer. A quantum computer, which also does have to be superconducting, but a quantum computer is actually something different that has to deal with the strange nature of quantum mechanics. But again, both of these things, a superconducting computer and a quantum computer, are both very challenging just because of how cold things need to be, and also makes it very expensive. So charging would in general mean that you're giving something a charge. So, back in the days when the Egyptians would rub material together and may not know what was happening, they were charging material. So if you take your wool and you rub it along a glass rod, you're charging that rod. And ultimately, this is charging by friction. One material, well, this isn't always true. I mean, rubbing wool on a piece of wood isn't going to have the same effect as if you rub it on a glass rod. But what happens is one of these materials tends to knock off the electrons. So when you rub the wool on a glass rod, this tends to knock off the electrons from the wool and onto the rod, and then that charges the rod. And you're doing that ultimately through friction. And that's what they're trying to say here, is that you can charge by friction, because friction might knock off some of the electrons. And I say might because it's not true for all materials. It does have to be pretty specific for what the materials are. And I guess they're just showing a silly little situation here. Or I guess she's sitting way far away and she slides over to give him a kiss, and that sliding over caused her to become charged, and then there was a static shock there. I get it, a funny little picture, but I mean, he's driving. It seems at least be parked or something. Seems kind of dangerous to be not even looking ahead there while you're driving. But that's what they're talking about here, charging by friction. That means rubbing things together. This is probably, I would say, our most common experience with electricity, and this is static charge. You build up static charge through friction when you're rubbing on stuff. Charge by induction. So this means then that, let's say I took this piece of wool, I rubbed it on this glass rod. So that dumped some of the electrons onto this glass rod, and now this glass rod has some negative charge to it. Q commonly used for charge. So this rod now has some negative charge on it. And what if I had some conducting sphere? Remember, conducting allows electrons to move. And I take my rod that's now negatively charged and I touch this sphere. Well, if I touch the sphere, now these electrons will dump onto the sphere. And that's what they mean by charge by induction then. Induction here means we're just touching. And that act of touching will cause the electrons to move onto the sphere. Now, if you're asking, well, why would they move onto the sphere? Well, if I have my rod, remember, electrons, they're the same charge. So they want to repel each other. And so the electrons will try to space themselves in such a way that they're as far away as possible from all their other neighbors. So in a silly sense, all electrons massively hate each other. and they don't want to be anywhere near each other. And so electrons are always trying to maximize their distance from everybody else. And then when you touch another conductor, well, this gives the electrons another place to escape to. And so if you would have these two things touching, well, now the electrons are going to spread over everything, because they're going to try to get away from each other as much as they can. And that's why the electrons would move onto the sphere when you touch it, because you're giving another avenue for the electrons to get away from each other. And that's what they'll end up doing. And then they move on to the sphere because they're like, oh, hey, here's another way for me to escape all you other guys there. And that's why they end up moving. Now, it does have to be a conductor. So if you touched an insulator, well, then nothing's going to happen, because an insulator resists charge moving around. Because in an insulator, the charge is really tightly bound. And so you would have to touch a conductor to get charging by induction. You'd have to be using conductors and not any insulator. And they are saying that if you charge an object near a conducting surface, is what they're talking about there. And they got some of the pictures there of just what I was just drawing here in the page. If you have a charge rod and touch it, it'll bring that charge onto the metal sphere there. And they're giving looks like a little example of lightning here. So if you have charge buildup, so if the bottom of the cloud, so try to imagine this, here's Earth, here's my cloud. Now if you're getting charge buildup like they're drawing here on the bottom of the cloud, just minus, if you get that charge buildup, what's going to happen here is the ground is neutral. Let's say it's got a plus and a minus, it's neutral. But this negative charge here is going to want to push away this negative charge. So what happens as a cloud charges and it gets this negative charge in the bottom is it causes the ground then to have the positive charge near it, because remember, the positive charge is attracted to the negative, and then it pushes the negative charge down because the negative charge wants to get far away from this one. And that's what they're trying to draw here with the ground, the Earth, how they're saying the Earth is positively charged here. I don't know if I would say that's necessarily true. It's just that the positive charge will come to the surface. The negative charge will be pushed down a little bit because, again, positive charge is attracted to the negative, so the positive wants to try to get closer, and the negative charge wants to get away. So the negative charge is going to try to move away from that negative charge in the cloud. And then you get this buildup. You get this buildup of minus and plus, and they want to attract each other, and then a lightning bolt is eventually when you get a breakdown of the atmosphere here, and then all the charge will release itself in a giant burst of lightning, and then all that charge kind of cancels out and goes back to neutral again until the process happens again of the buildup. Lightning rods. Why are lightning rods good? Because a lightning rod is a conductor. So electricity chooses the shortest path. So if I have my cloud here, and the electricity has a choice of either going to the ground or going to this conductor, it's going to choose the shorter distance here. It's going to go for the conductor. And that's why you like to have, with tall buildings especially, or just areas to protect from lightning strikes to the ground, good to have some lightning rods around so that if a lightning bolt strikes, it'll be attracted to the lightning rod versus, say, going towards the ground. And that's what you're talking about here is building here. Got the two lightning rods here. Something about Benjamin Franklin. Franklin, a United States figure, absolutely helped with the formulation of the electric field and electricity, but Franklin, not alone. There was many people that actually contributed to the development of electricity. Ben Franklin is one of them. Not trying to take away his contribution, but I certainly wouldn't single him out though as the sole contributor. There's actually many people that contribute to our understanding of electricity, and Ben Franklin is one of those people for certain. Now, charge polarization, now they're talking about a little bit more what I was talking about with the ground, how the ground tries to orientate itself so the plus is closer to the minus and the minus gets farther away. That's what they're talking about with charge polarization. So imagine I have a molecule and it's electrically neutral, so it has as many plus as it does minus. And then let's say I bring in a rod that's negatively charged towards this molecule. Well, that's not going to rip the molecule apart. The molecule is still going to stay a molecule. But what it's going to do, though, is it's going to align itself. It's going to say, whoa, I have this negative charge up here. My negative charge wants to get away from it, and the positive charge wants to get closer. And so the molecule will spin. It will turn to align itself with this magnetic field. And that's what they're trying to show here, that when you bring charge, that it could cause, we call this a polarization, that we're polarizing this molecule, that we're aligning it with this other electric field that's present. If you're curious about these pictures A and B, why are all these blue dots around? Well, now they're trying to give a more accurate picture of what the atoms actually look like. They're saying the electrons are buzzing around. The truth is that we don't know where the electron is. So if here's the nucleus, we don't know where the electron is around the nucleus. What we know is there's a probability of finding it, and we tend to call this the probability cloud. That the probability cloud, very dark near the center, but then gets lighter as you go out because the probability of finding an electron gets less and less. And we call that the probability cloud. And it looks to me that's what they're trying to kind of draw here, this probability cloud. Oh, they do say an electron cloud. Now, it's not like the electron is a cloud. The cloud part is the probability. The probability kind of forms this haziness around the nucleus of where you would find it. Looks like what they're trying to draw there. Microwave oven. Microwave oven is specifically designed to use microwaves to stimulate water molecules. And then the stimulation of those water molecules is what heats food. That's probably just what they're talking about there in their little side technology blurb. Here's another example of what I was drawing up here, that when you have a neutral atom or molecule and you bring in an electric field, that the molecule will align itself with the electric field. And that's what they're drawing here. You can see all of these atoms, they're all the plus is pointing towards the negative rod. So all of these atoms here are aligning themselves with the electric field. And we call that a polarization. That it's not that these molecules, this is still a total charge of 0, this molecule. Yet the electric forces will still cause an alignment of it simply because the plus wants to be closer than the minus does. And that causes then particles to spin and align themselves. And that's what they're drawing there. And again, we call that polarization. The particles are being polarized. These are actually really two good examples of a comb and a balloon. So a balloon, let's start with the comb. When a comb gets charged and you bring it next to a piece of paper, well, the piece of paper is electrically neutral. But this electric field causes the negative charge to be attracted towards the comb and the positive charge to go to the other end. And this does cause an attractive force then, because the negative is closer to the positive. And so that force is stronger than the repulsion of these pluses because they're farther away. And so what they're trying to explain here is, again, you can have material that has a net charge of zero. Net charge of zero, meaning it has just as many positive as it has negative. Net charge zero. But because they can become polarized, there can still be an attraction. Because when the particle polarizes, the plus and minus are closer. So this field, this force is greater than the force of the negative and negative. And so then you get an attraction. And this is why a charged comb can attract very small pieces of paper, not a large one. But and balloons, same deal. How is it a balloon can stick to a wall? Well, the balloon would first have to be charged, meaning you probably rubbed it or something. You build up some static charge on there. And if the balloon is negatively charged, it polarizes the wall. And remember, polarizing means it's still electrically neutral. It's still charged zero. But the molecules arrange themselves so that the pluses are closer and the minuses are farther away. And then that causes an attraction, even though the wall is electrically neutral. So the moral of the story here is that even something that's electrically neutral can have attraction because it gets polarized. And very common, so this is a picture of a water molecule, and same type of deal. You know, the pluses are way over here, the minuses are over here, and this causes the water molecule to get polarized. It can spin around, and even though it's electrically neutral, because a water has 2 positive and 2 negative, so it's charge zero, yet because these charges are separated, means that there can be an attraction. So let's see the electric field. All right, so the electric field. What is the electric field? And I would have to say, physically, that's a difficult question. I would say, what is the electric field? That's because in classical physics, the electric field is a vector field, where in quantum mechanics today, the electric field is actually an exchange of particles. Pretty wildly different pictures, although they are mathematically compatible. And for us, if you have a positive charge, what we say is it emanates an electric field, and it does it symmetrically. And now these lines I'm drawing are mathematical objects. So it's not that there's actually arrows that point out a positive charge. This is the math description we use. We call it a vector field, that these are all vectors that tell us the direction that motion will happen. So for instance, if I put a positive charge here, the positive charge will move along this field line. If I put a positive charge here, this positive charge here would be pushed along that field line. And the electric field is this field that exists in the universe, and then we try to describe it mathematically, and we do that with a vector field, is how we describe the electric field. Ultimately, they give us the force here. Now, let me just say this. Before, we saw force is K Q1 Q2 over R squared. What we end up doing in physics is we just peel off one of these E's. And so we end up peeling off one of these Q's, and then we have this. And then we call this the electric field. And so that's the statement they're showing right here, that the force is equal to Q times E. So every charged particle creates an electric field. And then another particle in that electric field will feel a force. They wrote E equals F over Q. Sure. Uh, the electric field, though, is commonly written as though KQ over R squared is the electric field from one piece of charge. And here they're showing the vector part. So these arrows are the mathematical representation. So I do have people in my 131, because that's where we talk about this stuff. They ask me sometimes, look, do these arrows actually exist in nature? And the answer is no. These arrows are a mathematical construct that we use to explain the electric field. And they are showing negative charge, so plus the electric field radiates outwards from that. For a negative charge, the electric field radiates inwards towards electric charge. And that's what they're showing here, a picture of negative charge. So they have the field lines going towards it. Over here we have now what happens if there's positive and negative charge. So something that happens with the math is these field lines can never cross. In other words, we can't have a field line cross. That can't happen with the math. And so what happens is these two field lines, as they connect, as they end up connecting like this, and that's the picture that they have that they're showing, that we get this field that looks like this when we have a positive and negative charge. That's this kind of video they're showing here. But I do want to show you another example. What if we had two positive charges? If we had two positive charges, the field lines cannot cross. So when you have two positive charges, well, this field line and this field line, they can't cross. And so they end up bending away from each other. And that's what ends up happening then when you have two positive charges, is these field lines will then bend away because they can't cross. And that's how we get, that's how we mathematically describe how these things repel then, or versus attract. And just to say it one last time, these arrows are a mathematical construct. It's not like these arrows actually exist. An electric field is nature's storehouse of energy. The electric field does store energy, but so does the gravitational field, so does the magnetic field, so does the strong nuclear force field. So it's not like only the electric field is a storehouse of energy. All fields are in physics. All fields store energy. And here's some more pictures of how. Now these I think are really cool. It's something I'm still trying to work on for actually in class, because I need strong magnets and charge here. There's actually charge and a lot of iron filings. But these are real pictures. I always think they're really cool because so they use little iron filings. You know, it's just a tiny piece of iron that's like a little rod, and then then there's just thousands of them. And if you take these iron filings, you just dump them. It's like kind of like a sand, and you just dump them down. They'll all align then to the electric field like this. And so I always think these pictures are pretty cool because it's like you're actually seeing the electric field, even though you aren't. You're just seeing these little iron shavings aligning themselves. But I still always think those are pretty cool pictures. These are actual pictures of what happens when you drop little iron filings down on something that's charged. All right, so I just wanted to read that a little bit there because shielding, might be feels a little bit too much for 101, but here we go. A conductor can have no electric field inside of it. So now an insulator can have an electric field inside it, but a conductor can't. And the reason this happens is because if a conductor has charge on it, then the charge wants to get away from itself. Again, let's just use negative charges, but they dislike each other in this weird sense. They want to be as far away as they can from each other. And this causes a cancellation of the electric field in a conductor. In other words, all the charge, as it gets as far away as it can from all the other negative charge, causes the electric field then to be canceled in the conductor. And what we say is that this charge resides on the surface, right at the surface of whatever our object is. And then the electric field inside is 0. And what they're showing with this yellow object here is that if we have, say, a cavity that's got negative charge in it, well, this is a conductor. This is a conductor. It won't allow an electric field in it. And so what will happen, let's say there's 2 negative charges here. Well, what will happen then is 2 positive charges will come against this surface. And then you have 2 positive, 2 negatives. The net electric field here will be 0. And that's what they're talking about here with these charges at the surface. So right up here, they're saying the charge gathers on its outer surface. And again, it's because the charge is pushing itself away. They're trying to get as far away from each other as they can. And so if you have another charge sitting right here, well, it's not going to feel anything from this because there's no electric field in the conductor. A conductor aligns itself. All the charge in a conductor aligns itself. So there's no electric field in the conductor. And now they are showing 2 cavities in this picture, just to try to, I guess, complicate it a little bit more. But same is true with 2 cavities. If you have a charge here, you'll get charge buildup here on the right on the surface, causes the electric field to cancel within the conductor. And so if you have a charge sitting here in the conductor, it won't feel any electric field from any of these because the electric field is 0 in a conductor. And that's the idea they're trying to get across here. Would have been nice maybe they showed a few charges on the surfaces here so we could kind of see it instead of just this kind of yellow-orange picture. But that's what they're talking about. Electric field is 0 inside a conductor. Not the same for an insulator, though. Insulators can have an electric field in them. Is that... No, it's not Tesla. I don't know who that is. Tesla, Nikolai Tesla, is famous for doing these types of experiments. There's actually a really cool picture of Nikola Tesla where he has these giant generators, these Van de Graaff generators, and they create these giant kind of like mini lightning bolts or really giant sparks. And he's just sitting in his cage reading a book, and all these giant lightning sparks are just surrounding him. And what Tesla did is he actually created a metal cage. In this case, we have a metal car. Metal is a conductor. So when this lightning bolt, here's my car, it's just this rectangle. When the lightning bolt or this giant spark hits the car, well, metal is a conductor. And so it won't allow any electric field inside of it. Now, inside of it is where the person is. And so that's this person right here. They're inside the conductor. And inside a conductor, there's no electric field. And so that's why this person is safely sitting in the car while this giant spark hits the car. It'll look really fast for this picture of Tesla. And, just typed in Google Tesla and cage. And these 2 black and white ones, this is Nikolai Tesla with all the absolutely crazy amount of electricity. I mean, if any one of these bolts actually hit him, that'd probably be instant death. This one's interesting too. This person here standing in a very, very small Faraday cage is what these are commonly called. Well, you can see the lightning hits the cage and they're safe inside there. Just other pictures here of people in a Faraday cage. Here's another person standing in a Faraday cage as the lightning strikes the cage. And again, what is happening here is this metal cage, this cage is metal. Metal is a conductor, and this person is, in a sense, standing inside the conductor. And inside the conductor, there's no electric field. And that's how people can safely stand. And here's a drawing just of a person standing inside the conductor, and then the electricity hits the conductor. All the charge goes on the surface, and there's no electric field inside the conductor, and so the person is safe. And so crazy pictures. Nikola Tesla, and did some crazy stuff. There's I can't remember. Let me see. I think this is this guy, man, this guy's crazy. Now I say crazy because he does stuff with electricity that I myself would not be brave enough to do. But if you want to see some just really crazy stuff with electricity, this styropyro, it's taking a while to load up there. But this styropyro on YouTube, a very knowledgeable guy about electricity, and he does some really crazy stuff with electricity that I don't recommend doing, but it's interesting to watch him do some of these things. And that page is not loading, but styropyro, I guess I'm inadvertently promoting his YouTube channel, but I have to say he has some really, really fun videos with electricity that I think it's all electricity that he does, but he did a video where he had 100 car batteries, and the amount of electricity that generates just destroys material because the current is so high, it just melts material. And I think that's what his last video was that I watched. 100 car batteries, and then he would just put current through material, and the material would just absolutely evaporate. It's pretty wild. And in this last picture, they're just showing how charge accumulates. If you have a nice round sphere, everything can move equal distance from each other because ultimately the electric field is spherically symmetric. So you get a nice symmetry when you have a round object, where once you break away from that, charge does accumulate on corners. And that's what you're just trying to show here, that charge does like to accumulate on corners like this, just showing those different objects. And the last part is electric potential. And I have to say, this one really scares me in trying to talk about without referring to math. But let me say this. I got to say something about math because the electric potential is ultimately a result of math. And we can measure the electric field, but we tend not to. Instead, we tend to work with voltage. Now, voltage is electric potential. So when you see your device and it's got a 9-volt battery, well, volts is electric potential. And now there is an unfortunate phrasing. Electric potential is voltage, but right here it says electric potential energy. This is energy. This is energy. That's not voltage. So we have these two phrases. We have electric potential, which is voltage, and then we have electric potential energy, which is energy in joules. So these are two different things, but the wording makes them appear very, very similar, and so that can get confused. Voltage is not energy, but this isn't on any of the homeworks or anything. I just want to give you some idea of what the truth is. But the electric field is this vector field. And it turns out that the electric field has a special mathematical property that, and now this is some calculus here, but we can describe the electric field as the derivative of something that is just numbers, and we call that voltage ultimately. And I know I'm going well beyond the math of our book here, so again, not in the homework or anything, but the reason that we've gone with voltage is because dealing with voltage is actually easier than dealing with the electric field, because the electric field is a vector, and a vector contains a direction and a magnitude, where voltage is just a magnitude. There's no direction to it, and that makes it mathematically easier to deal with. And this happens to be just a fact of nature and a fact of math, that the electric field turns out to have a very special math property that allows us to describe the electric field in a simpler terms mathematically, and that simpler thing is this function that we end up calling voltage then. And I would argue that is the ultimate source of why we have voltage today and why we don't measure the electric field, is because it turns out to be mathematically better to use voltage. And they're trying to explain voltage in some intuitive way, and that's where I struggle with things, because, I think the result of voltage is purely mathematical, and how you can give an intuitive description of that is always a challenge, I think. But if you want to check that out, read that here. They're going to try to give you an intuitive description of voltage, and check that out. But I would say this: what is the best thing to perhaps remember for a 101 level class is that voltage is how we measure the electric field. And I think that was the last one, so we'll check out the homework. All right, so let's check out what number one's got to say. Which part of an atom is positively charged and which part is negative? Well, the center of the atom is where the positive charge is located, the nucleus. And again, it's there because the protons, which are the positive charge, are much, much more massive than the electron. The electron is just like this tiny thing way out here. So the positive charge sits at the center. The negative charge is what is flying around it. So what do we got? The nucleus is positively charged, and the electron cloud is negatively charged. Now let me just say this about what they're saying, electron cloud. By cloud, they mean probability. From quantum mechanics, we don't actually know where the electron is. We have a probability of where it is, and that probability is what is called the electron cloud. So it's not like I don't know, maybe it is. It's still debated on what this probability means. But the electron cloud, I don't think of as an electron, say, in some cloud, like the electron's now this fuzzy cloud thing. I personally don't think of it that way. To me, the electron cloud is this cloud of probability. And you know what? Let me show you a picture of that. All right, so now the simplest picture of an electron cloud is like this one right here, this black, where it's very dense towards the center because that's where we expect to find the electron in the highest probability. And then the cloud fades out as you go farther away, meaning it's less probable to find the electron. Now the spherical shape is, we call it the S shell. It's not the only shell, though. And what's cool over here, this picture here, I don't know if I can get that any bigger there, but this picture here is actually what happens because there's higher states the electron can be in, and these are all probability clouds. This is where the electron is. Now these brighter colors is where the electron is most highly expected to be found, and then the blue is still where you could find it. So this in the top left is the lowest state, and then as you go to the right and then down, these are higher energy levels at the, in this case, they're talking about hydrogen, higher levels that the energy can be in. But I just want to try to, again, I'm going a little bit behind the book here, but just to state this again, the nucleus is at the center, and this picture that the electron orbits is just a simple picture we draw to try to convey the idea. This picture here is what the probability actually looks like. And you can see it doesn't really look like, in some cases, like these down here that are kind of flower petal looking, that doesn't look anything like some circular orbit. So these probability clouds can look very interesting. These patterns can be very interesting. And this is just for hydrogen. All of the atoms have their own different probability clouds. So this is what's meant by the electron cloud. Is the electron actually this cloud? I tend not to think so. These clouds are ultimately from the math that is a probability. These clouds represent the probability of where to find the electron. And that's what the clouds actually look like. So our answer here is the first one. The nucleus is positive, and surrounding that is what's negative. Let's see. What is a positive ion? What is a negative ion? So an ion again means that an atom likes to be in a neutral state, meaning if I have 3 positives at the center, there's going to be 3 electrons in the orbiting around it. That's the state matter prefers to be in. But things happen in nature, and maybe this electron might get kicked out. Well, if this electron gets kicked out, we have 3 positive and 2 negative, which means this would have an overall charge of plus 1 E, and we'd call that a positive ion. That's what we'd call that. Now, sometimes this can actually capture an extra electron. And if that's the case, then we would have more electrons than protons, and we get an overall negative ion. And that's what they're talking here. The positive ion means you've lost an electron, and a negative ion means an atom that gained an electron. So let's see what our choices are here. A positive ion is a neutral atom. Oh, that's wrong. A positive ion is a neutral atom. Oh, these all start with neutral atoms. Oh, and it has gained or lost. All right, I see. So they start as a neutral atom, and then something happens. So a positive ion has gained electrons. No, a positive ion is something that lost electrons. So our second one says that a positive ion has lost electrons. A negative ion has gained electrons. So that looks good. Let's see what the others have to say, though. This last one, this one says neutrons. Now remember, neutrons are neutral particles. They don't have a charge to them. So this one's wrong because a neutron has no charge. And the last one says a positive ion is when you lose a proton. Well, losing a proton at the nucleus is an entirely different story because that involves nuclear forces then. Much easier to knock these electrons out. Very difficult to knock these protons out, though. Knocking these protons out, this is where you're starting to deal with a nuclear energy and atomic energy and nuclear power and that type of stuff. So, what is an atomic bomb? Well, an atomic bomb is where you're actually trying to break apart this nucleus. So this last part here, when they say that is lost a proton, now we're into the nuclear bomb territory where you're destroying the nucleus. That is much, much more difficult to do. That's not something that just happens. Well, I was going to say happens naturally, but that's not true. The sun is a giant nuclear reactor. It's actually fusing things together. The sun is actually, what happens with the sun is when you have nuclei, is the sun actually forces them together and creates a larger nucleus, which creates a heavier element then. So the sun, all stars are actually doing nuclear fusion where they fuse nuclei together to make a larger particle. That's fusion. So that's where you got the U in there, fusion. This, if you want to get rid of one of these protons, well, that's fission, where you're breaking it apart, you're fizzling it away. And so that's nuclear fission, breaking apart the nucleus. Nuclear fusion is when you're combining nuclei together. So our answer here is the second one. What are materials such as glass and rubber good insulators? Why are materials such as glass and rubber good insulators? Insulators, again, insulators have tightly bound electrons. Tightly bound. So right here, electrons are loosely bound. No. Electrons are loosely bound. No. The last are tightly. Electrons are tightly bound. So it's one of these last two. Making them good conductors. Heat. I don't know why all of a sudden they have gone to the word heat here. But okay. Insulators are poor conductors. So insulators, electrons tightly bound, poor conductors is what we have there. The main thing I would say about insulators is insulators don't conduct electricity. There's no current that flows through an insulator because the electrons can't move. And current is the motion of electrons. So when you turn on your light bulb, that's electrons moving through a conductor. If your light bulb was connected to an insulator, it would never turn on because current can't flow through an insulator because the electrons are too tightly bound to the nucleus. What kind of charging occurs during thunderstorms? We did talk about thunderstorms. What type of charging? They gave us two types of charging. They gave us charging by friction and charging by induction. The cloud's going to be charging by friction. This first one. Charge is delivered to clouds when gamma rays from space. Okay. Well, I don't even remember that being talked about in the book. All right. Here we go. Here's charging by friction. Charging by friction. Charge by contact. That's where we have charge by induction. And here again, charge by induction. So the other one we have here is charge by friction is the second one here. Clouds are charged by friction. Things, rubbing against the clouds, removing electrons or gaining electrons. So clouds charging by friction. Electric potential. Unlike electric potential energy. Electric potential measured in volts. So just to say this again, because this is one of those things in physics that always likes to be emphasized, I guess, is that we do have these two sayings very close to each other, but they mean different things. Electric potential is voltage, like your 9-volt battery. Volts is the unit of electric potential. Electric potential is us measuring the electric field, where electric potential energy is in joules. That's actually this first one here, in joules. And that is an energy then. But electric potential itself does have units of voltage. And let's just take out this last one. Okay, the only one with Coulomb's law. So Coulomb's law is, what are they writing here? Coulomb's law is the force of the electric field is this K number, charge 1, charge 2 over R squared. This is Coulomb's law. Now, more specifically, Coulomb's law does have this 1 over 4 pi epsilon, Q1, Q2 over R squared. This is the more official form. This is kind of the simpler form right here. Now, whether it's much simpler, I mean, not too much. All we're saying is K is 1 over 4 pi epsilon naught. But just looking at our choices here, we can see this third one is the only one correctly written. You can see these other ones are not written as KQQ over R squared. So just by looking at this, we don't even need to pull out our calculator. This is the only correct one, this third one here. And that's the homework. Talk to you in the next video.